And this is the story of how the Finch was designed. The Finch stems from the CS-Bots program at Carnegie Mellon's Create Lab. CS-Bots, started in 2006, aimed to reverse the decline in computer science enrollment. Our hypothesis was that using robots as objects for students to program could improve retention by demonstrating to introductory level students that their programs could create real-world results. We also thought that some students would learn better by being able to see a physical world representation through the robot of their programs. We began our design process by collecting information about the problem through a number of activities. We started by looking at the few previous studies that had used robots in computer science. We then improved our own understanding of the classroom realities that introductory computer science educators face by conducting phone interviews with 37 such educators teaching at 2- and 4-year colleges. Through these interviews, we found that most educators would be interested in using teaching tools, including robots, to improve retention, and that most also could not change much about the curriculum they taught or the programming language of the class. We also analyzed the top 10 textbooks used in introductory CS at the time to grasp how introductory courses typically progress through common CS concepts like variables, classes, and iteration. After these interviews, we began a process of participatory design with teachers at a local community college and at high schools across the U.S. The purpose of the participatory design step was to determine what robot features and capabilities were necessary to support introductory computer science educations, and which ones were not. In our pilot work, we used a very feature-rich and fairly expensive robot built from off-the-shelf parts. This robot used an iRobot Create as its base, but also included a speaker, distance sensor, wireless link, webcam, and light sensors. In participatory design, we try to involve the end users, in this case teachers and students, as much as possible in the design. So we conducted a full semester-long pilot in the fall of 2007 at a local community college with the robot, where students used the robots for nearly all of their assignments. We also conducted more limited pilots in 2007 and 2008 with 20 teachers nationwide, and each teacher was provided with one robot. Teachers worked with us to design the software API and also to develop the curriculum. In summer of 2008, we came up with the design constraints for a robot that, based on all of our sources of information, would be beneficial in introductory computer science. We determined that, first of all, the robot should enable individual ownership and home use. So this means that at least at the college level, students should be able to take it home, use them at home, and that there should be sufficient robots so that each student should be able to have a robot. In order to enable that, we needed to make the robot low cost enough so that this works within either student budgets or classroom budgets. The robot needed to be portable. It needed to move from the classroom to the dorm room and back. The robot needed to be robust enough to survive that trip and also to survive call it the home environment. And the robot needed to support multiple platforms. So it needed to work with the computer at the student's home or dorm room. We also found that the robot should be aesthetically appealing. One of the strengths of robotics is that when students and others see the robot moving around and doing what they programmed the robot to do, it can form sort of an emotional connection between the student, their program, and the robot. We see this when people start referring to robots as he or she instead of it. And when you make the robot more aesthetically appealing, you can strengthen that connection. The robot should be richly interactive. We found that it didn't matter so much which features our robots had, just that a potential robot needed to interact with the student along as many of their senses or with as many of their senses as possible. So it should engage them through motion, but also through light, through sound, by having them pick up the robot and do something with it. The robot needed to just work. So we couldn't have a case where a hardware failure on the robot prevented a student from completing an assignment. And finally, especially what we found through the phone interviews is that in order for a potential robot to have wide adoption as a teaching tool, it needed to support existing computer science courses. You couldn't create a whole new curriculum around this robot. So based on those constraints, we designed the Finch, which is a low-cost robot for computer science education. Our target price was $99, roughly the cost of a college textbook, and we do actually sell the Finch for that amount. The Finch is portable. It's supported on the 3 most common operating systems, and it works in over a dozen languages and programming environments. It's also robust enough to survive lots of use and abuse. In terms of capabilities, in addition to moving around, the Finch has 2 light sensors, a temperature sensor, 2 obstacle sensors, and a 3-axis accelerometer. The accelerometer allows the Finch to sense its orientation. In this video, the color of the Finch's beak is changing based on which direction the Finch points. This sensor can be used to turn the Finch into a game controller, with the Finch's tilting and rolling causing the movement of a cursor or other graphics on the screen. We also take advantage of computer speakers wherever we can to produce speech, play music, or play tones. And the Finch itself contains a small beeper for local sound creation. To summarize, here's how the major design choices of the Finch allowed us to meet our design constraints. First, the Finch's tether, which was the most controversial of our design choices, allows us to meet cost, portability, and multi-platform support constraints. It also minimizes the potential failure points on the robot and makes it unlikely that the robot will just stop working due to hardware problems, because the Finch is sort of the minimal set of things that you could have and still have a robot. In terms of rich interactivity, this is achieved by a suite of sensors and outputs that, while fairly low cost, also engage with the human senses of sight, sound, and touch. The plastic shell makes the Finch aesthetically appealing, at least in our opinion it does, and it makes the Finch robust, as you saw in the video before. The shell was actually designed by a professional industrial designer, and she drew up 9 sketches, and we sent those sketches to our partner teachers and had their students vote on the sketches, and the final shell is actually the combination of the top 2 vote getters, so it's essentially student approved. Finally, the cross-platform and multi-language support allows the Finch to be integrated into existing courses without significant changes being made to those courses. So thanks for watching this video about designing the Finch. You can learn much more about the Finch at www.finchrobot.com.